So step one is to download, install, and configure HDX-MS v3. So here I've already downloaded it. So depending on which site you're downloading from, you'll either have a macro-enabled workbook or a zip file. If you have a zip file, you'll need to uncompress that. So if you do a right click and say extract all, it'll extract to its own folder. And you can go into that folder where you'll have that macro-enabled workbook. And if you double click on this, it should automatically recognize it as an Excel file and load it into Excel. And for today, I'm going to be using Excel 365 for all the demonstrations. It will work fine in 2016, and it may run fine in previous versions of Microsoft Excel. I just haven't tested it. So in this case, when we try to open it, you see this red line that the macros have been blocked. This is a security feature. Unfortunately, with this, a lot of the features won't work. So the workaround is to go to File, Save As, and if you save it as any other file name, I'm just going to add a letter to it. You can close this version, and if you open the version that you saved yourself, it may look different. So here in this case, yep, we have this splash screen popping up, HDX-MS v3. If you dismiss this, now all of the macros should be available to you to use. There are a couple of other settings you'll have to change. So if you go to File, down to Options, in here, if you go to the Add-ins option on the left, and down at the bottom where it says Manage Excel Add-ins, if you hit Go, you'll want to make sure that you have Analysis Toolpack, Toolpack VBA, and Solver Add-in all checked. You'll need those for full functionality. There's one more thing we have to fix. So if you go to File, Options again, and now if we go to the Trust Center, into Trust Center Settings, if you go to Macro Settings, you'll want to make sure that you have this Enable VBA Macros set. Sadly, you'll have to do it this way to make sure all the macros are going to be able to run properly to process all the data. And also check these lower two for the 4.0 macros and the Trust Access to VBA project. The last thing you have to set up is permissions within VBA. So to get to that, you'll want to go to the Developer menu item. If you don't see a Developer menu item, then you have to go back to File, Options, and here if you click on Customize Ribbon, you want to make sure that you have the Developer here on the right side checked. If it's not there, you may have to drag it over from the left and enable it. But once that developer is enabled, you should have access to the developer menu item here. And from there, you can launch Visual Basic. So if you click there, it opens Visual Basic. And here there's an option to go to Tools, References. And in there, you want to make sure that you have Solver and this ATPVBAEN XLS both checked. You'll need those again for full functionality of everything that we're going to be doing in HDX-MS version 3. Okay, so once those are set, you can close out of VBA. I would hit save to make sure all those settings are saved, and now you're ready to process data. So once everything is installed and configured, now this HDX-MS window should have an additional menu item here for add-ins and an HDX-MS option here. And this has all of the features that you need to process data through HDX-MS. So the first step to processing data is to pull in your spectral data into Excel, into the format that HDX-MS can process. So what that's going to look like is this XY format where the X dimension is your M over Z, and the Y is intensity. And for each pair of columns, it's going to be associated with one spectra. So in this case, A and B would be, say, the undeutorated. The next two would be a time point, another time point, or fully deuterated, and so forth. And here's an example of what a full data set ready to process would look like. So here I have a bunch of pairs of columns that have that XY data, M over Z and intensity, and the very top row is the label of what they are. So in this case, you have the undeutorated, a TD, which is a fully deuterated, and various time points. And these labels are very syntax dependent, so you have to put them in just right. And if you're not sure about the syntax, you can go to add-ins HDX-Express and use the add exchange time labels function, and this will guide you through the labeling process. So in this case, that first pair of columns is going to be an undeuterated, so if you click undeuterated, it'll label it. The next one's a fully deuterated, and then we had a 1 minute, a 2 minute, so you can keep going through and labeling each of the time points here, and once you're done, you can hit finished. The one thing I will point out is for HDX-Express, it won't accept duplicates. So if you have, say, 2 1-minute spectra in there, you can't label 2 of them 1 minute. The trick I use is to basically label one of them 1 minute and label the other something like 1.01. And that'll get around that problem. So just a heads up on that. So once you have the data formatted and labeled, it is ready to process. To process the data, you have the window open that contains all of the data you just imported. You go to add-ins, HDX-Express, and you use the Analyze Spectra option. This pops up a window that has 2 tabs, Analysis and Output, and you have to specify all the information for the peptide that you want to process. So in this case, it's asking for the charge state, which in this case, it's a 2+ ion. The distribution width refers to how low in the relative intensity of the peaks you want it to analyze for width. 10% is a good safe bet. Use isotopic peak detection, I would have selected unless you are processing really noisy data or data that is at really low resolution, which would be kind of exceptions nowadays. If you are importing data that has already been centroided or stick data, then you would want to use this feature and not this feature. And I'll have an example of that later. But for now, everything we're looking at is profile data, so we're going to want isotopic peak detection, and it's not already centroided. Down here, these are tolerances related to peak picking. So this refers to how much of the base peak intensity it's going to consider to be a peak. I like to have this pretty low, so it gets kind of some of the weaker shoulder peaks. And M/Z refers to how many data points from the peak center it's going to look at when it decides where the peak apex is. And this is kind of dependent on the resolution of your instrument. I think 6 for TOF data is a good starting point. For Orbitrap data, you might have to go lower. There is one feature down here for trimming spectral data. So sometimes the output XY that you get, depending on what mass spec software you're using, will not already be zoomed into just the spectra that you want to process for that peptide. So if it, let's say, gives you the whole M/Z range and you only want a small portion of it, which I highly recommend trimming, or this is going to take a long time, you can use the trim spectra data option and specify where you want it to start and where you want it to end. So for example, if I wanted to do that here, I know for this peptide, there's going to be nothing of interest below 1 or below 785, and there's going to be nothing above 795. So that way I can trim out any M/Z data points above and below this. But this is already trimmed to what I need, so we don't need to use it in this example. And then in the output, you can decide how you want it to report the deuterium uptake. So you can say either absolute in Daltons, relative deuterium, so everything has a subtraction from the undeuterated, or percent. By convention, I've used relative deuterium level for everything. And this is the time units that it's going to report the results in. Down here, you have the option to plot the width of the isotopic distribution, which could be useful in assessing whether something looks broader than expected in terms of the isotopic distribution. You also have 2 functions here that you may or may not need. So apply smoothing, you will sometimes need if your data has a lot of noise or is really jaggedy and peak picking may be thrown off. I highly recommend smoothing before importing into HDX-Express. A lot of the mass spec software has more elegant smoothing algorithms. This one's kind of a canned one that works if you need it. And there's also a baseline subtract feature. So if you know you have some kind of weird baseline distortion in your spectra, If you want to try it, you can, but again, this is something that I highly recommend using whatever baseline subtract features are in your mass spec processing software, because they're probably more refined and elegant. So for now, I'm going to leave those unchecked, and everything else is good, so we can say OK. And now HDX-MS will start to process each of those spectra. It's going to go through, it's going to pick all of the relevant peaks, and it's going to identify the geometric center of each of those spectra. And then at the very end, you'll end up with a new workbook that has a summary worksheet here, which is popped up by default, and then a worksheet for each of the spectra that it processed. So here, sheet 1, unduterated, it's showing you the unduterated spectra and all of the peaks that it picked. The green is the geometric centroid, and the orange is the width of the distribution of the isotopic peaks. This is the fully deuterated, and then you have this for all your time points as well. If we go back to the summary, you can see here this is the deuterium level, or the D uptake plot. So this is deuterium level relative to the unduterated as a function of time. This looks a little different because this is actually not time-based deuterium exchange data, so normally you'd have an uptake curve that starts low and reaches high. And then the plot on the right, which is not updating correctly, but this is showing you the width of the isotopic distribution for each of those time points. And then all of the centroid data, basically the summary of everything, is up here. So this is all the geometric centroids for all your spectra, and then the isotopic widths for all your spectra, and then these are all the time points with the fully deuterated at the end. So this summary already has all the geometric centroids for the spectra, but the whole point of HDX-MS version 3 is to be able to do binomial and multimodal analysis. So after this initial processing, you can go back and do a second round of analysis by going to Add-ins, HDX-MS, and selecting Binomial Fitting. Here it pops up a window where you'll need to specify the number of amides. This is the number of slow exchanging sites that can get deuterated in your peptide. I recommend leaving this at 0, which will automatically estimate this from the peptide sequence that you put in. And I also recommend checking this optimize fits box. This will automatically vary this number of amides parameter to try to get you the optimal fit. Below that, for fitting asymmetry, this is a function that most people will not need unless they're dealing with really overlapped data. If you want more information on this, then I recommend looking at the 2013 JASMAS paper on HDX-MS version 2. That's all described in there. And for most things nowadays, we tend not to use it. Below that, in this box, you can choose to either read the unduterated mass envelope from the spectrum for the unduterated spectrum that you uploaded, or you can calculate it from the sequence, which I always recommend doing. So if you're selecting that, you'll need to provide the peptide sequence here. And I'm going to copy and paste in. This is glufib. So here is the sequence we're going to put in. If you have a glycopeptide, you can use this function below to add glycosylation and specify the formula here. Or if you have any other custom modifications, like let's say you had an acetylation or phosphate or something like that, you can basically just add the formula of what you want to add. Or if, let's say, you had some kind of a loss, you can always just have a negative sign and then say, for example, H2. If, let's say, you had something like an internal disulfide bond or something like that. So we don't need that for this example. And these parameters here and below, these are for only fitting to raw spectral data. These will only apply if in the initial analysis you did not use that checkbox for peak isotopic peak detection. This I seldom use anymore. It sometimes is helpful for really noisy data. However, if your intent is to do multimodal analysis, this is not going to be a very practical approach. So we're going to not focus on this for today. So once all these parameters are up here are set, you can say OK. And now HDX-MS is going to go into some more elaborate calculations where it's going to use a couple of algorithms to predict the natural isotopic distribution of your undeuteurated peptide. It's going to use that information to then apply binomial fits to each of the spectra that you've input. And depending on the speed of your computer, this could take a couple of seconds, or it could take maybe up to a minute, depending on how many spectra you've input. I do recommend running this on a relatively modern, high-powered desktop rather than a laptop. It's possible to run on a laptop, it just might take a lot longer to get through some of these calculations. So down here at the bottom left, you can actually see how it's working. This is where it's trying to optimize the fit for each of the spectra that it's fitting. And in this case, I think I have 20-something spectra, so this might take almost a minute to complete. Okay, and once it's done, it goes back to the summary worksheet where now it added more data and more windows. So again, you still have that D uptake plot here, except now the black is the data from the original geometric centroids, and now the blue is from the binomial fit analysis. And that summary sheet now contains all that information up here. So it added data for columns E and F, which are the labeling probability and then the relative deuterium uptake from the binomial fit in F, and the number of amides for those parameters, or for each of those fits, in column N. And it also, now in the width plot, it's showing you the original isotopic width in black, and then now in blue it's showing you the number of amides used for each of the fits for each of your time points. And then lastly here, so once the calculation finishes, it goes back to the summary page, and now it has made some additions where now for the deuterium level, or the D uptake plot, it's showing you both the original geometric centroid in black and now the binomial results in blue. So this is the D uptake from the binomial fits. For the width plot, it's still showing you the original isotopic width in black, but now it's also showing you the number of amides used for the best fit in the binomial fitting process for each time point. And then this third plot is again just a D uptake plot, and this will be more relevant once we start using the multimodal fitting approach. So for now, you can ignore that. And then up here in the summary, now it has all of the original data that we had in the first analysis, but now it also has columns E and F, which contain the labeling probability and the relative deuterium level from the binomial fit in F, as well as the number of amides as the best fit parameter for each of the time points in the binomial fit. And if you look at all of the individual worksheets, you can see that now, for all of the time points, there is also this purple fit, which represents the binomial distribution that was fit to your data. So you can see that for each of them, hopefully, it's giving you a fit that's very much consistent with the distribution of your isotopic peaks. And one thing to note here is that next to this binomial, there's a number. This corresponds to the number of amides, which is actually up here in cell I3, that gave you the best fit. The number in brackets is the maximum expected number of amides from the peptide sequence. So here it's saying it's 13.5. 13 is about what we would expect. Here's an example of a spectra that's clearly bimodal, and it was not able to fit this obviously, so the binomial in this case just fit to one of the two populations here. And that's why this has a 10.6 number of amides. But if you look at something like this, or a better example is where you have something that is multinomial, so this is two populations that are not well resolved, And here, what the binomial tried to do was to fit as best as it could to this distribution, but as you can clearly see, it's not a great fit. The number of amides that gave the best fit was 23, which is way higher than the expected 13. And when you have a case like this, the spectral title is actually flagged as red and bimodal, indicating that there is evidence here that this is not a unimodal profile. So as you go through the data, you can basically use this as a way to flag anything that looks potentially bimodal. Sometimes it's blatantly obvious and you can see them by eye, but sometimes it's relatively subtle. And this may look unimodal, but based on the binomial fit, it took way more number of amides than is theoretically possible in this peptide to give you a good fit. So this basically tells you that this is way too broad to be a unimodal fit that's consistent with EX2 kinetics. So this is the first step that you can do to basically fit everything and test whether the spectra fit to a unimodal population or not. So now the next thing we can do is go to each of the spectra where we suspect that it is not unimodal. So these look okay. Okay, here there's a clear bimodal that is clear as day. And what you can do to analyze this is go back to add-ins. So again, you have to be on the worksheet that you want to process, HDX-MS, and then now we're going to use the bimodal deconvolution menu item. This is going to pop up another window where you can specify how you want to do the multimodal fitting. So at the very top, you have a double binomial and a triple binomial option. So you can do a triple fit if you suspect there are 3 populations in there. But if you want to do that, you first have to do a double. And then after the double, you can try a triple if you're convinced there are more than 2 populations in there. Below that, there's some options that you can use. So you can use a perform bimodal statistical analyses, which does some statistical analysis after the fitting to assess whether the parameters are of high confidence or not. You can do an iterative analysis where it will essentially fit multiple times, incorporating small amounts of error to the spectra, which you can also use to determine how confidently this can be fit. And lastly, there's this apply multimodal fit to all spectra. If you have this checked, it'll basically go through all of the worksheets here, except for the undeuteriated and fully deuterated, and it'll try to apply a double or triple binomial fit depending on which button you push. Below here, iterations and percent error, this is related to the iterative analysis. So this is basically how many times you want to refit, and this is how much error you want to input at each iteration. I highly recommend 20, which is the maximum that is allowed in the software, and 30% from our experience seems like a good number to use for this iterative analysis. So for now, what I'm going to do is do a double binomial. I'm going to perform the statistical analysis, and I'm going to perform the iterative analysis. So when you hit this, double, it's then going to start another series of calculations to fit this spectra in many different ways and establish how well it can fit 2 binomial spectra to it. And this again can take a couple of seconds, or it could take minutes depending on how many iterations you're doing and how fast your computer is. I think on this medium powered laptop, this might take almost a minute to do with 20 iterations. So once the calculations are done, this worksheet should look something like this, where now the spectrum has been updated to show you the 2 best fits. So here now you have a green for the fit of this first population and a light blue for the fit of the second population. And in the inset, you have the corresponding p-values that are associated with either an f-test that tests whether fitting 2 binomials versus 1 binomial is justified. So that's this first one, f-test p. So the lower that number, the more evidence that there is for being able to fit 2 binomials instead of 1. So anything with a p-value under of about 0.05 is deemed to be significant evidence that you have not just a single population. So that's something that you can use to further justify fitting 2 versus 1 when you're analyzing the spectra. Down below, fit 1p and fit 2p, these are p-values associated with the parameters that are used to fit these individual populations. So the lower these numbers, the more confidence you have that these are actually well resolved and you can pin down exact parameters associated with each of those populations. So anything about less than 0.01 is a pretty confident p-value. So that's reported here in the inset. And then this result will also spit out this iterative fitting box because we did 20 of those iterative fittings. And this is basically the summary of that. So what you're seeing here is an XY plot where the X dimension is the deuterium level of each population. So this one's the green, that's the first one. This is the light blue, the second one. So this is the relative deuterium level for each of those. And the Y-axis is the relative intensity. So how much of the total intensity are each of those populations taking up. And this should be about 50-50, and you see that that's exactly what we're seeing. And the fact that they're clustering really tightly means that in all 20 of those iterations, you were getting about the same answer, which is something you can use to assess how confidently you can really assign all the parameters associated with each of those binomials. And all of the information from that iterative fitting is summarized down here. So this is cells G39 to 45. So this is the deuteration level of your first, your second population. This D3 currently is meaningless. This is designed if you're doing a triple fit. But here's the average of all the values and the standard deviation. And then this is the relative intensity. So this is for each of the first and second populations. And then again, this is standard deviation, which you can see is pretty low compared to this number. So this is an example where you have a clearly resolved bimodal, really easy to fit, really easy to extract information from both populations. So what we can look at is a few other examples where the populations aren't nearly as well resolved. So let's look at some of those other time points. And I went ahead and I did the same type of double binomial for all of these. So here's an example again where you have 2 populations in there. You can kind of see that by eye. But now with this double fitting, you can actually get some numbers to evaluate how well can we statistically evaluate whether we have 2 populations in there and whether we can extract information for each of those populations. And you can see from the iterative fitting, the spread is still okay, not as good as for the other one because this is not nearly as well resolved, but still decent. So this you can still reliably interpret information from. But let's look at some other ones where that might not be the case. So these are all still pretty well resolved. And here we're getting to one where it's not. So here, this is still 2 populations, but they're really poorly resolved. So by doing the F-test of the single versus the double fit, you still get a really strong p-value, further telling you that yes, this is multiple populations, not just a single population. You are justified in using 2 populations to try to fit this. But what you see now is that the p-values for those individual fits, they're starting to get pretty weak. So in this case, the p-values associated with this green population are no longer significant. And the corresponding iterative fitting window also shows that. So if by introducing a little bit of noise into the spectra, you get wildly different best fits, this is telling you that you really can't interpret any of the information for each of those fits with any confidence, really. So the deuterium level that it's putting out for the green population, it's a best guess, but you really don't have the resolution to pin that down very accurately. So this is an example where you could use these tests to say, yes, it's not unimodal, there's more than one thing happening in there, but we don't have the level of information to confidently be able to fit 2 things and assign anything for each of those individual populations. In some cases, what you'll see is that when you try this double binomial fit, you'll see that there's still more to the spectra than just the two states you're trying to fit. And here's a very blatant example of where we actually have three populations. And when you try to fit to two, it does best it can, but it's still not able to really capture the isotopic profile with just two distributions. And here what you'll see, I mean, in this case you see it clearly. Sometimes what you'll see is that the p-value for the f-test isn't that great because it's just unable to achieve a great fit with two when there's clearly more than two populations in there. So in this case, what you can do is try to see if maybe three populations is able to fit this data adequately. So you can go back to add-ins, express, bimodal deconvolution, and instead of doing the double binomial, for this one we're going to apply triple binomial. And again, you only want to apply triple after you've already done double. So once you've done the double, you can select that worksheet and then hit triple. And this, again, depending on how many iterations you're doing, could take half a minute to a minute, depending on the speed of your desktop. Once the calculations finish, it'll update this worksheet. And now you see that in the spectrum view, you have three populations. You have the green, the light blue, and now the tan for the third population. And you can see by eye, this three binomials fit the spectra pretty well. And if you look at all of the statistical analyses, this top f-test P, this is the f-test comparing the double fit to the triple fit. And you can see that this p-value is really low, indicating that you have high confidence that fitting with three populations is justified. And all of the individual p-values for the parameters associated with each of the fits are actually all pretty nice too, indicating that you have high confidence in the relative intensity and the deuterium level for each of these. If you look at the iterative fitting plot, you can see that there's three populations there now for deuterium level and relative intensity, and they're clustered relatively well. There's one or two outliers, but not much. For the most part, they seem to agree, and all of that data is summarized again down here in this box, where you have the average and standard deviations for the deuterium level of each of the three populations and the relative intensities. So in this case, this is something that actually looks like it fits well to three, and you can really characterize each of those subpopulations really well. But let's see what would happen if you overfit. Let's say you had only two populations and you tried to fit three. So we'll go back to that first example. The 4-minute time point is what it's labeled here. So this is what fit well to two populations. And when we try to do the same triple fitting approach, what we see is, well, yeah, it's able to fit three populations to it. So we have that first population fit to a single, and now this second distribution here, it's kind of splitting it into the light blue and the tan distributions. But when you do the statistics, you see that that f-test is now no longer significant, so it can't justify 3 versus 2 binomials for this spectra. And also, if you look at the individual p-values, you see, yeah, there's still high confidence associated with this green because it's a unique profile that it's fitting to a single species. But the other two, the blue and the tan, you see that there's basically zero confidence. It's a p-value of 1, indicating that you should not interpret anything about these relative deuterium levels or their intensities. And you can see this in the corresponding iterative fitting plot. You have great clustering of this green population, but the blue and the tan are all over the place because there's infinite ways to fit two populations into here, and you're not even justified using 3 versus 2. So once you've done all of the fitting for every spectra that you spec as multimodal appropriately, what you will lastly want to do is to summarize all of that data in the summary sheet. So if you go back to add-ins, in bimodal deconvolution, there is a summarized double and a summarized triple option. So if you've only used 2 binomials or double fits for anything, you can use double. If you use 3 for any of them, you'll want to use triple. So if you hit that, it extracts all of the information from the new fits that you did, and it incorporates it back into that summary sheet. So we're back at the summary sheet, and now you can see it's basically filled in a whole bunch of these cells. So now instead of just showing you the binomial information for the first fit, It's now in G and H showing you the labeling probability and average deuterium for all your time points for the second fit and the third fit here in I and J. And then K, L, M, these are the columns related to the relative intensity of each of the three populations in those triple fits. And N, O, P are the information for the number of amides used for each of the populations that were fit for all of the various time points. And all of the plots below are also updated. So now it's showing you the binomial fit for all three populations, including the original centroid fitting. It's showing you in the width plot all of the number of amides for all your time points for all three of the populations that you were fitting. And lastly here, this additional plot is showing both the deuteration information for all three of those binomial fits for all your time points, and that's here in the x-axis. And then there's a corresponding dash line that is the y-axis label here, which corresponds to the relative intensity of each of those populations. And we'll see in a second how this can be really insightful. So now let's look at some practical examples of what fitting real bimodal data will do and how to interpret the results. So here's another data set that's already imported and labeled, ready to go. So we can do that initial centroiding analysis, analyze spectra. We'll need to specify the charge state. This is a 2+. We're going to use peak detection, just 1% for that base peak intensity. 6 is fine. Okay. When it gets through this initial round of analysis, it'll create that new workbook and the summary page. So here we are. And you can check, make sure all the data got processed right. You can clearly see that there are two populations in there, and the fully deuterated looks like a unimodal profile, which is what you expect. So next we can do the binomial fitting. So again, you have to specify the number of amides. I'm going to put 0 and optimize fits so it'll automatically calculate that. I'm going to use the sequence, which I'm going to paste in. That's the peptide sequence, no glycosylation or modifications. Okay. So now it's going to do the routines for the binomial fitting. There's not that many time points here, so this should only take, I don't know, 10 or 15 seconds or so. And once that finishes, you should see the summary worksheet. Okay, there. So it popped up the summary worksheet. So now this has all the binomial information in it as well. And if you go through all the worksheets, you'll see that, all right, there's the purple fit of the binomial. You can see it's unable to fit the full profile because there's a second population in there. You can see it even more in the later time points. So now what we can do is for every time point where you see it's bimodal, you can go in and do a bimodal deconvolution and apply a double binomial. I'm going to use the statistical feature here. I'm not going to do iterative analysis just because I want to do this relatively quickly. So let's apply a double. So for a single iteration of a single spectra, this should only take a couple of seconds. Okay, there. So you have the green population and that light blue population. We're going to do the same thing. There's a keyboard shortcut you can hit. It's Control-Shift-D. Will automatically do the same thing. It'll apply a double fit to a given worksheet that you have active. So I'm going to do this 2 more times for that 30-minute and the 20-hour time point. Then we'll summarize the data and we'll see what it looks like. Yep, still looking okay. And here's the last one. Okay, so all the time points are fit. The undeuteurated and the fully deuterated are unimodal. So now I'm going to go back to bimodal deconvolution and say summarize double. And now we'll go back to the summary sheet and you'll have all the information there from both populations that you fit. So let's focus in on this third plot here. So what this is showing you is that the deuterium uptake of the blue population, which is the first binomial, and the deuterium uptake of the second binomial, the red. So here you can see that both of them are taking up more deuterium over time, although the blue is the more protected population, the red is the less protected population. And the dashed lines here for the red and the blue, these are actually what are really informative, because this tells you that the relative size of the blue, or the first protected population, really isn't changing over the time course of the experiment. So it's up around 0.7 something here, and it kind of stays there for all the other time points. And you see the same thing. The red population's pretty small, and it stays that way. So this means that over time, the relative intensities of the protected and the not protected population don't shift. So this is not EX1 kinetics. So what this actually corresponds to is two different non-interconverting conformations that are present for this sample, and you're basically able to probe EX2 exchange for both of them. So if you look through the data, that's what's happening. These population sizes really aren't changing relative to each other. They're both just getting more deuterated through probably an EX2 mechanism. So if you see something that looks like that, then you have a mixture of different conformations that are not interchanging. Let's look at one more example. So here again is all the data that's been imported into Excel and labeled, ready for processing. So same routine, analyze spectra. In this case, this is just a 1+. So after you go through that first centroiding step, you have the summary, okay? To make sure that everything got picked all right. And in this case, it's a little more subtle, but it is definitely still multimodal. So we're going to apply the binomial fitting next. Binomial fitting, number of amides, we'll let that optimize, and we'll paste in the sequence of the peptide. No modifications or glycosylations, so okay. Again, there aren't that many time points, so this should take 10 or 20 seconds to get through all of these. Sometimes these clipboard errors come up. It shouldn't affect how well the calculations work. It's just something with certain versions of Excel that tend to happen. Okay, so here's the summary. Okay, so it's showing you the result of that single binomial fit, and you can see if you look across the actual time points, you can see that the single binomial was not able to really capture what this isotopic distribution looks like. So that's, again, evidence that there's some kind of multimodality here. So let's start using the double tool. Bimodal deconvolution, we're going to be doing a double, and might as well do the statistics. And again, I'm not going to do iterative analysis right now just because I don't want this to take a long time. However, if you're not sure about how well the two populations are separated, I would recommend using that iterative analysis function. Okay, so there. The p-values don't look amazing, but it was able to fit two populations relatively well. So let's keep going. With smaller peptides, it's kind of harder to get good resolution between the two populations. So yeah, these p-values are kind of right on the borderline. I'm going to use that Control-Shift-D shortcut again. And two more. You can see down in the bottom left, this is all of the iterative, well, not iterative, this is where it's trying to do the minimization to get you the best fits. All right, last one. It is reassuring to see, though, that as it's going through all the calculations, it's not just hung up. Okay, there. So now we're going to summarize all of those double fits. Summarize double. Okay, cool. So now when you look at the summary, what you see is that you have two populations, the blue population, which really isn't ever or is barely deuterated and doesn't really get much deuteration over time, and the exposed population, which is already highly exposed even at the first time point and then basically stays that way. So instead of those changing, what you're actually seeing is the relative intensity of both of those populations changing. So the protected population starts off a little high, so right around almost 60% of the total. And over time, it shifts. So you have this population dropping out and the red population growing. And this is what we classically associate with EX1 kinetics, where you have this population shift from low deuteration to high deuteration across the time points. So this is a good example of that, where you see the dashed lines changing rather than the deuteration of each individual population. Okay, this next example is going to be for using HDX-Express to process pulse labeling HD data. So this is not continuous labeling. Here we're perturbing a protein and then doing a rapid labeling step to basically label whichever populations were present at that given moment. So this data is already processed, it's been imported, it's been through the initial centroid analysis and through the single binomial fitting. So if you look at the data here, this is the undeuteurated reference. The 1 second time point is actually not a time point, this is a reference. This is a fully unfolded version of the protein. And then all the later time points, this is where it's had time to refold. So this is after 20 seconds of refolding and so forth. And you can see from the single fit that there are multiple populations in there because you're probably probing an unfolded state as well as a folded state, which is changing over time. And that's really what we're trying to get at with this type of pulse labeling data. So here, you could do the same approach we've seen before where you, let's say, just want to apply a double fit to this. So let's do the statistical analysis and we'll say double. Again, I'm not going to do iterative analysis because it's going to take a while. Although I highly recommend using it if you're not sure, especially if you don't have great resolution between the two populations that are in your spectra. But if we just do a simple double binomial fit, we can see what we get. And this shouldn't take too long for a single iteration. Okay, so it was able to fit two populations to it. You can see it looks pretty nice here. The FP test is good, so you have great confidence that you're justified using two populations instead of one to fit. But if you look at these p-values for the individual parameters, these don't look great, meaning that you don't have good confidence in the relative intensity or the deuteration level of either one of those two populations. So this is an example where, because we know it's pulse labeling and we have a reference of the starting point, we can actually do a little bit of tweaking to how we do the fit, and we can restrain some of the parameters. So if we go back to that 1 second time point, we know that this is our fully unfolded version of the protein, and it was pulsed the exact same way and run the exact same way as all the other samples. So what we can do is look at cell I3. This is the number of amides for the best fit. So that's 5.82. And we can also look at I8, which is the cell that has the labeling probability. So if we remember those two numbers, we can actually restrain them for the fits of all of the later time points. So if we do that, we'll go back to where we applied the double fit. There. Now if we go to bimodal deconvolution, instead of doing the double binomial up here, I'll uncheck the statistical analyses because they won't work for the restrained fitting. So now if we want to restrict and not vary one of those parameters, we can basically insert a number other than 0 here. So what I'm actually going to do is put in that labeling probability and the number of amides, so the P and the N value that we got from the fully unfolded reference spectra. And I'm going to set those as the second population, just because the second population by convention and the way I'm analyzing this is going to be the more deuterated species. And I'm going to leave 0 for the labeling probability and the number of amides of the first population, because that I want to vary and try to achieve the best fit. So once you put all those in, you can hit restrained double down here. And this algorithm is pretty much just like the other binomial or the other double binomial fit. It's just going to restrain whatever you've told it to restrain. And everything that's a 0, it's going to not. So here's the resulting fit. Again, these p-values don't mean anything anymore because we're restraining. But now you can see that it was able to use the information from that fully unfolded labeled state and then basically fit whatever other population was in there. So if we go and do this basically for all the time points, one of the ways we can do that is go back to bimodal deconvolution. And if you check this apply multimodal to all spectra, it'll basically save you the work of going through sheet by sheet doing this fit. So if you check that, hit restrain double, it'll apply this with the same restriction to all the spectra except for the undeuterated. Just keep in mind it'll also try to do this for that 1 second time point, but we'll just be mindful of that. So this may take a little over a minute to do. Okay, so all the fits just finished. It's on the last time point now. And if you look through, you can see that it was able to restrain that second population and fit whatever it could to the first one. So now if we want to look at what the total data looks like, you can go back to bimodal deconvolution and you can use that same summarize double function to summarize all of those multimodal fits into the summary page. Cool. So here that is, and we're going to be focusing specifically on, again, this third plot. So this is now showing you the deuterium level of basically both populations that it was able to fit, and this is showing you the relative intensity of each of those populations. And in this case, that's more what we're interested in, because we have, in this case, probably 2 states where you have a folded and an unfolded, and really it's the transition and how that population shifts that we're interested in. So in this case, for example, this red curve would be the transition from the folded state or the unfolded state to the folded state, and then blue would be the inverse. So if you want to get all these numbers, again, they're right here in the summary. So for each of your time points, this is the relative intensity of the first and the second population. And what I would recommend is basically using HDX-MS to do these fits and then extract this information and do whatever other analysis you want to do with whatever tools you generally use to fit folding or unfolding data. If you want to do a kind of a quick fit of this, there is a function down here for basically just fitting exponential, either a single or a double exponential to this type of data. So for example, let's say we want to look at the change in the first population, so the population in blue, and we want to fit that to a single exponential. If you hit this, it'll populate there it goes. It'll basically populate another plot here off to the right. It's called EX1, but it could be used for pulse labeling as well, where it'll plot the population size, in this case, of the unfolded population over time, and it'll try to fit, in this case, a single exponential, but you can also do a double exponential. And all the parameters associated with that fit are up here. So it basically filled in all of those cells to do this. But again, this is just kind of a tool there if you want to do a quick and dirty fit of what you're getting. And for anything publication worthy, I would recommend taking this to something more formal for that data fitting. So the last example I'll show here is for data that you're importing that's already been centroided. So in this case, it's basically pre-centroided or stick data, as some people call it. So now the X values and the Y values are still M over Z in intensity, but this is now no longer profile. It's just centroided peaks and the total intensity, which is still fine. So HDX-MS can handle this, but the only difference is that when you do the first round of analysis on here, so when we go to analyze spectra, we want to uncheck the isotopic peak detection and say that the data is already centroided or stick data. And in this case, the charge state still needs to be specified. Everything down here will be grayed out and we're not trimming it. So if you say OK, then it'll recognize that this has already been centroided. So there really isn't much peak picking to do. So here you can see that it's able to pull in the data. It looks wonky because now it's already centroided, but you can still use this and apply the same binomial analysis. So you could do binomial fitting the same way, 0, optimize fitting, calculate from the sequence, and I'll paste in, this is still glue fib. So aside from already being centroided, the rest of the algorithms should work seamlessly, and every multimodal analysis should still work seamlessly. So here's the first binomial. So you can see that it was still able to fit that just fine. It still gives you a warning if things are broader than expected. So you could still go in and do the same exact bimodal deconvolution, double, let's perform statistical analysis. And all the statistics, just like with profile data, should still be valid. Yep, so here you can see the fit was still able to do what it needed to do. It's still showing great p-values. So if you have centroided data that you're working with or stick data where you're working with, you just have to make sure that in that first step for analyze spectra, you're using the right checkboxes here. So you don't need the peak detection, data is already centroided. There's a couple of additional features within HDX-MS that might be useful here and there depending on the situation. So for example, here is an example of a spectra that's undergone the initial processing, but it missed this peak here, which you may want to include. It's a useful piece of data. So one of the things about HDX-MS is basically everything you're seeing in the plot is here within the worksheet somewhere. So in this case, all of these points in red are actually up here in columns D and E. So this is the X and the Y. So if, for example, we wanted to incorporate more points into this, one of the tricks you can do is basically select the last two, and this will autofill to the next one. But as you can see, it won't let you. So by default, when HDX-MS processes sheets, it locks them. So there's a tool within HDX-MS to unlock worksheets. You could do this through Excel too. It's just a convenient way to unlock all of the worksheets across the whole workbook. So that way, if we wanted to do this, and let's say we wanted to add another peak in there, we can do that. We autofill down, and then if we float over it, we can get that the apex intensity is 16.49, and we can manually add it in there. It won't be included in the plot because by default the plot is only going to plot what was there originally, but we can add it if we really wanted to. So now when you do the binomial fitting approach or any kind of bimodal analysis, you'll have a more complete set of peaks to actually fit to, which can be helpful sometimes. And other times you might have situations where you have spectral overlap and one of the peaks didn't get picked right. if you need to adjust it manually before you do the binomial fitting, it is possible. So that's another feature. There's also a resummarize binomials feature. This is if you ever do complete a bimodal analysis and you summarize it, but then you want to go back and tweak some of the individual fits and change some of those numbers, you can use this resummarize binomials to update the summary. So then all of these values here will be up to date after that. The last one I'll point out is this get spectra from mass links. This is only for users that have waters data and that are processing it in mass links. There is this tool that if you have mass links open, you can actually use this to directly import XY information from spectra open in mass links. However, this is kind of an old feature. It will only work if you're running 32-bit Windows with 32-bit Excel. Most newer builds of Excel are 64-bit, and this function is no longer going to work. Plus, most waters users are probably going to have ion mobility enabled data, in which case you probably can't use mass links. So this is just good to be aware of for in case you're just using non-mobility data with waters. This may come in handy, and this is actually described in one of the earlier publications for HDX-MS, the original version 1. So the last thing I'll cover is what if you want to use HDX-MS to analyze something that's not a peptide, which is totally possible. There's just a few tweaks you have to make. So here, for example, I have data for a small compound that's undergone HD exchange, just a couple of time points. The first step is basically identical as you would process peptides. You need to set the charge state. We're going to use isotopic peak detection, leave everything else as is. So through the initial analysis, you can see, okay, it worked. It was able to find the peaks in the spectra. And again, this is for a non-peptide small molecule. So what's different about processing this is for the next step, when you want to apply the binomial fit, you no longer have a peptide you can specify down here, and you will actually have to specify the number of amides you want to use because it's not going to be able to estimate it from the peptide itself. So I think for this, let's say it's 6. We can still optimize fits. You can say calculate undeutrated from sequence, but for peptide sequence, we're just going to put in a minus sign. Then the program will know to ignore it, and it's basically going to rely on whatever you put down here as a custom modification for the formula for the compound. So I'm going to paste in the uncharged, basically the formula for the neutral mass of this compound, because HDX-MS is automatically going to add an extra proton knowing it's a 1+, so you'll have to put the uncharged formula down here. And I will note that this will also work for negatively charged molecules, but what you'll have to do is you'll have to subtract 2 protons, well, depending on how many negative charges there are on it. And it's always good to check to make sure that this formula you put in is accurate, and I'll show you that in a second. So for now, okay, we've checked the custom modification, we've added in our formula, and we have this minus sign here. So let's say OK. It's going to go through the binomial procedure. There's only a couple of time points, so this won't take very long. Okay, and here's the summary sheet. So now if we look at what it did, okay, here's the purple fit, is that binomial fit on the undeutrated. And this is the cell you want to check. Cell I2 is the monoisotopic mass it calculated from the formula that you put in. And you want to make sure that this is right. Because if you're off by a proton or something, the binomial fitting is not going to work. So you want to double check that cell I2, make sure it's right in the undeutrated spectra. And then later you could see, okay, it actually was able to do a pretty good job fitting the data. So that's really the only tweak you need to do to get this to analyze other things beyond peptides. And all of the other functions which you can use for peptides will still work. If you want to do double, triple fitting to this data, at this point, that'll be identical to what you did for treating it like a peptide.